This figure shows three-state Markov model for EI system with hot standby, which is a randomly changing dynamic system. The main components of this Markov model are states and transitions and transition rates. So this is state one, the fully operational state, that is the initial state, where both system A and system B, that is the main system and the standby system, are working. This is state two, where only standby system, which could be system A or system B, as the case may be. This is state three, which is the shutdown state, where both system A and system B are not working. So now the transitions, as you can see, you have from state one to state two. This is a transition with arrow towards state two, with a transition rate 2 lambda, which is labeled on the transition. It is 2 lambda because any one of the state or any one of the system A or system B can fail. So they add the transition rates add, and so the transition rate is 2 lambda shown here. In the event in the state one, in the event of safe detected common mode failure, then there is a transition from state one to state three in this, as you can see here with the arrow towards this, and that has a transition rate called lambda common mode, which is common mode failure, which is assumed as 1 in 2 years, and when translated per hour, it is 0.406 per hour. Similarly, in the event of detection of a failure, safe detected failure while in state one, based on the internal diagnostics coverage, then there is a transition from state one to state two. In this way, it goes to transition with the transition rate 2 lambda, where lambda is the failure rate of a system A or system B, that is once assumed as once in 3 months, based on the field data. And the field data, based on the field data, this values of the failure rates and recovery rates, which are the transition rates, are taken and are given in this table. While in state two, that is in the event of a safe detected failure, there is a transition from state one to state two. While in state two, that is in standby, the standby tries to restore the failed system A through mu1, mu2, mu3. mu1 is the auto reset recovery of a system, which on average takes 10 seconds, assumed as 10 seconds. That comes to 360 per hour. That is the mu1, that is the auto reset recovery rate. In case the auto reset recovery fails, then minor repair mu2 is attempted. Minor repair rate of a system is average 30 minutes, that is 2 per hour. In the event of in the event of failure of minor repair, then the major repair mu3 is attempted, and a transition from state 2 to state 1 occurs via the mu3 after the major repair. So while in state 2, if in the event of safe detected failure of system B, that is standby system itself, before the repair of the main system, then there is a transition from state 2 to state 3. It goes to shutdown with a failure rate lambda, which is labeled here. And after going to shutdown state, the AMC representative is called, and he will come and attend the shutdown repair in on average 4 hours, and on the repair of safe shutdown repair, then the transition occurs from state 3 to. In this way, the Markov process moved from state 1 to state 2 to state 3 based on the random events of failures. As you can see, There is a transition rate on the label on each transition. Like here, you have transition rate mu1, mu2, mu3, and another transition lambda, mu shutdown 3, shutdown repair, which is also a transition rate. Transition rates are failure rates and recovery or repair rates, which govern the length of time that elapses before the system moves from the originating state to the target state, which is also called target state. From the originating state to target state, governed by 2 lambda. This is also called the state transition rate is also the state holding time, governs the state holding time. And state transition rate are the key in our objective of computation of probabilities of being in each state at steady state for investigations of reliability. In this slide, we describe the stochastic Markov process, which is the essential component of Markov. You can see that the system enters state 1, that is the initial state, as we can see the initial condition, and it spends an amount of time called the holding time. In this case, in state 1, the state holding time is T1. It spends some time in T1. It starts from state 1 because the initial condition, there is probability of 0 of state 1 is 1 and the probability of being in other states 0. Therefore, it begins with state 1 as per the initial condition and it stays until state holding time T1. So the system enters state 1, spends an amount of time equal to T1, the state holding time, T1, which is a continuous time random variable, and then jumps to another state, that is, it jumps to state 2, and it stays, spends an amount of time in state 2, which is state holding time T2, then jumps to another state, that is, jumps to T3, where it stays for some time until it reaches the state holding time of that state, that is T3, and then spends time in another state. Then it comes back to state and it jumps from state 3 to state 1 and spends another holding time and then jumps to another state. It can go back to the same state also. So it jumps to the another state and so on. This process, this stochastic process for jumping from one state to another state, based on the state holding time in each state, is called the Markov process. As you can see, that each state has a Markov as a state holding time. The state holding, you can see that the T1, T2, T3 are the continuous time random variables which changes with time and which have exponential distribution. T1 is state holding time. You can see that the state holding time T1 is the exponential of outgoing transitions of state. So T1 is a continuous time variable with probability distribution, with exponential probability distribution. You can see this. This is exponential holding time is a exponential probability distribution with the outgoing transition with the transition rates of the outgoing transitions as parameters for the exponential distribution. Like for example, here the state holding time. So you have two outgoing transitions from state 1 to state 2, that is here, and then you have from state 1 to state 3 another transition. The parameter of the first transition is 2 lambda, and the parameter of the second outgoing transition is lambda common mode. So T1 is equal to exponential of 2 lambda plus lambda common mode. So it stays here, system the Markov model stays here, and uh, based on the exponential distribution of the parameter, so it 2 lambda now and lambda common mode. It takes the minimum of the two. That is the exponential the value of 2 lambda is considered, and the exponential value of lambda common mode is considered, and whichever is less, the holding time will, the holding time set to whatever is less. So these are called this is called competing exponentials. There is case of competing exponentials. So T1 equal to exp of 2 lambda and lambda common mode, which are competing exponentials, and the holding time will take the minimum of the uh, competing exponential and accordingly make a transition. If the exponential of 2 lambda is less than the exponential of lambda common mode, then T1 will be equal to exponential of 2 lambda, and so the system makes a transition from 1 to 2. Similarly, in T2, there is competing exponentials. They have exponential of lambda and plus mu system recovery. So there are two outgoing transitions, one here, one from 2 to 1, another from 2 to 3. So again, whichever is less, whichever is the minimum of the two competing exponentials, the state holding time will take that, and then as soon as that state holding time is reached, then it jumps to that particular through that particular transition through that with that parameter of the transition. It goes from state 2 to state 3. If exponential of lambda is less than the exponential of mu system repair, then it goes from state 2 to state 1. But if exponential of system repair is less than the exponential of uh, uh, lambda, that is the failure rate of system, and it moves to. So in this way, the Markov process moves from state to state, and the state holding time will give the probability of being in each state, because the probability of each state will change with time, and because it depends on the exponential value of the outgoing transition, which is a random variable, so it changes with time, and so the probability is also going to change. Now, what we are interested is a transient solution and a steady state solution. In the transient solution, what we are interested is for a given time t. That this process, the migration of this process, from state to state, uh, for a given time t, uh, is of consequence, as we are interested in the probabilities being in each state at the end of time t. So the transient solution of the Markov model will help us to find out the probability distribution at the end of time t. From the probability distribution, that is the probability of being in each state at the end of given time t, we can find out the reliability. We can obtain the reliability and everything. In the case of steady state, the changes in the probabilities in each state will not change. They'll be constant, and uh, they remain stationary. So in steady state, this Markov process will move from state to state and migrates. The probabilities also change, but finally they reach a steady state, that is with the stationary distribution. Under the as per the stationary distribution, we get the probabilities of being in each state, and from there we get the reliability and availability. This is how this is the intuitive explanation of the Markov process. In the next slides, we actually see how we compute them with the help of matrices. Elements of state transition rate matrix Q for the case study. The three-state transition diagram is shown below. Q is the matrix Q is an array of numbers which describe the rate at which the Markov model transition between states occur. You can see that the transition between state 1 and state 2 is 2 lambda. The transition rate between state 1 and state 2 is 2 lambda. As you can see here, state 1 and state 2 is 2 lambda. Similarly, the transition rate between state 1 and state 3 is lambda common mode, which is shown here. We also see the condition that the sum of the numbers in each row in Q has to be 0. So this 2 lambda plus lambda common mode, you add them both and give a negative sign here that is given in the diagonal, that is in the first element. And so if you add all these elements, it will come to 0. In this way, we set the state transition rate matrix Q. In this slide, we obtain the steady state solution of the Markov model, three-state Markov model, where pi 1 to pi 3 are the steady state probabilities, the state probabilities being in states 1 to 3 respectively. And we have equations pi 1 plus pi 2 plus pi q equal to 1, pi q equal to 0. Solving these two above equations, we get pi 1, pi 2, pi 3. We got pi 1, pi 2, pi 3, and from there we get reliability pi 1 is equal to 0.96984, availability is equal to 0.971. So this we get the reliability and availability. You can see that the impact of changes in on the failure rate of system on the reliability is less than the impact of change rate of system shutdown. Change reliability is some reliability at the end of using, which is 1 year of operation. You can see it. So in this way, we see that when we're changing the values of only one parameter, this sensitivity analysis is only for change of one parameter, that is at a time, failure rate of one system, and failure rate of shutdown. It's not for changing both the parameters. This does not. It is only a sensitivity analysis per parameter for a change of parameter. So the impact of change in shutdown rate, that is major repair rate, is more than the impact of change in failure rate of a. This slide gives analysis of results of steady state solution through migration of probabilities. The Markov model of system will contain a single initial state which represents fully operational system. In this case, it represents state 1. The initial condition is given here. The probability of being in state 1 is 1 in the initial state, and the probability of being in state 2 and state 3 is 0, 0. Now, from this initial condition, as time progresses, the probability migrates from the initial state to other states of the model based on the Markov process, which moves from state to state uh, based on state holding time, which is a random continuous time random variable with exponential probability distribution, which was explained in the earlier. So the probability migrates from the initial state to other states through the transitions. It moves from one state. The probability moves from one state to another state to here through the transitions at a rate determined by the transition rates labeled here. Lambda is one rate, transition rate. Lambda is another transition rate. Lambda shutdown is another transition rate. So let us say, for example, if you see the failure rates here, if you look at this table here, you can see that the failure rates here, lambda equal to 0.0046, and for the processor for system failure, failure of a system, and a common mode failure when both the system A and system B fail, are very low. System failure of lambda is 0.0046, common mode failure at 406. Whereas the recovery rates are, mu1, mu2, mu3, mu shutdown repair, they are very. So with the result, the states on the left, the probability will migrate to the states on the left because the failure rates are are low. The movement to the right are low, whereas recovery rates are very fast. So probability will probability of migrating to states on the left will be more than the probability of uh, moving to states on the right. For example, from the fully operational state, if there's a failure, it goes to state 2. But because of the very fast recovery rates, it quickly comes back to state 1. So in that way, the transition in that way, based on the data you have, the failure rates and the recovery rates, the probabilities will change from state to state. So eventually, it will come to steady state where it will come to steady state, that is pi 1, pi 2, pi 3, where the probabilities don't change. The probabilities assume a stationary distribution. Therefore, at steady state, the probabilities of the stationary distribution is defined as pi 1, pi 2, pi 3, where pi 1, pi 2, pi 3 are steady state probabilities of being in 1, 2, 3. So from the initial condition 1, 0, 0, the probabilities will migrate to different states based on the state holding time, which is a random variable, and eventually it reaches steady state. So at steady state, we have the system reliability, the probability of being in state 1, and system availability, probability in being in state 1 and state 2. So that is how you explain these values here. Very high values, as you see, because the failure rates are very low and the recovery rates are very fast. In this way, we analyze this slide gives the expansion of three-state Markov model, which we have described as a case study, with the addition of an unsafe state. Like you have three states here, and we are adding an unsafe state, state 4. So in the event of an unsafe failure, then there is a transition from state 2 to state 4 with a transition rate lambda THR, which is the threshold hazard rate for SIL4 equipment, which is 10 to the power minus 9 per hour. Similarly, from state 1 also, there can be a transition based on the threshold hazard rate for SIL4 from state 1 to the unsafe state. And once they reach the unsafe state, there are no outgoing transitions from state 4. There are no, you can see that there is no outgoing transition from state 4, and that state 4 is called the absorbed state. So in this way, we can expand the three-state Markov model. This is another example of expansion of three-state Markov model to 6 states. Now, we are partitioning the 6 states into internal states, which are inside the system, and external states, which are for external actors, that is for SM, ESM, AMC representative, and also for ES. So we have added extra states. We have expanded it to know how to model the external actors, that is station master, ESM, and AMC. We are modeling it with external states for external actors for repair and restoration. We can also see that in the internal state, there is auto reset recovery. See, from state to standby to standby, as we have discussed before, through auto reset, the standby system can restore the failed system, failed main system. So mu is the auto reset recovery, which is automatic. So that is how it is. That is how this we can model the internal states as well as the external states and find out the probability of being in each state. That way, it will help the administration to quantify what is the reliability and availability. The only thing is that these failure rates have to be correct. Like lambda alert 1 is one failure rate, lambda alert 2 is alert 1, the alert rate, and lambda alert 2 is another alert rate, then lambda minor failure, lambda shutdown, and then recovery, mu1 and mu2. So in this way, we can model the external state. Main thing, the accuracy depends on the failure rates and the recovery rates. As you can see, a model is an approximation. Is an approximation. The accuracy of results depends on the assumptions of failure and also on the matrix condition for matrix. If the data is accuracy of field data is not there, then results also will not be there. We are assuming that the failure rate, repair rate are constant, which in practice may vary with season. In the rainy season, failure rates may be more. Inter-arrival failure, repair, recovery rates are assumed to have exponential distribution, which may not be true in practice. The failure rate may not be constant, so the exponential probability distribution may not be applicable. In this way, these are some of the limitations of Markov. Philosophy of life in Markov model. State of mind should always depend on the present state of life and not on past states of lives and not on how we have arrived at the present state. The difficulty, it is difficult to follow in real life with the society around.